Okay, so we are going to get into how do we define directions in a unit cell. So crystallographic directions are important, and they're going to be very important because they're critically important to how dislocations move, how atoms diffuse through material. So we need to be able to kind of denote them. So for directions, we always use these square brackets, and we're going to develop essentially these Miller indices, and we're going to use basically this notation to denote basically your X, Y, Z axis or your 1, 2, 3 axis. So it's a lot of 3D visualization. So if you are artistically inclined, this may be relatively straightforward, but even so, it's really important that we kind of do this systematically, and we apply this consistent kind of framework. So let's say this is my unit cell. This is my unit cell, and I have basically this is, X, Y, Z. I always like to do 1, 2, 3. You'll also see in locations H, K, L. But again, I know lots of notation, but we'll get it. But this is our origin. So the origin when we're drawing directions never changes. Oops, I'm going to undo that. The origin never changes. So this is our, basically, the location 0, 0, 0. And this is going to be location 1, 0, 0. This will be 0. Okay, let me do. Excuse me, this is live. Oops, undo. So I don't like that. I like to do opposite. This is going to be 1xh, right hand, 2yhk. So this will be 1, 0, 0 direction. This will be 0, 1, 0. This will be 0, 0, 1. So let's say I wanted to draw the 1, 0, 0 direction. Whenever I do crystallographic directions, it's a vector. So we have a start and a finish. So to create this crystallographic direction, I need to do finish minus my start. So if I want 1, 0, 0, I can start or finish at 1, 0, 0, and I could do minus 0, 0, 0, the origin. So I can draw this right here. So you can see that there. But I could also equivalently, let's say my finish vector is here. So let's say my finish is at, this would be 1, 1, 1, minus, so if I want to get 1, 0, 0, 0, 1, 1. So 0, 1, 1. So this would be my start. So this would also be the 1, 0, 0, 1, 0, 0 direction. So this is the kind of procedure that we're going about doing this. So drawing is always a little bit more difficult. I think that if you're just looking at the vector and identifying, it can be a little bit more straightforward. So let's go ahead and let's do some identification of some vectors, and then we'll draw some, and we'll show some tricks. So let's get at it. So let's do some identification. So I'm going to draw and use some different colors. And I'm just gonna, let's say I'm gonna go from here to here. I'm gonna go from here to here. And I'm gonna go, let's do 4. I'm gonna go from here to here. And then I'm finally gonna go from, let's just do here. Let's go from here to here. All right, so let's figure out these directions. So remember, origin is still the same. So if I want to do my green, what is my finish location? Finish would be at 0, 1, 0. That's the point right here. Minus my start, which is at 1, 0, 0. So that would leave me with 0 minus 1 is negative 1. We denote negative numbers with this hat. So the hat here. Then 1 minus 0, 1. And then 0 minus 0, 0. So that would be my solution here. Let's go to our next one. Let's go blue. I'm going to do a little bit bold. So where's my finish? My finish is at 1/2, 0, and then 1. Where's my start? My start's at 0, 1, 1. Now, let's just write it out first. So I'm going to have a half minus 1 and then 0. I can't leave it in this reduced form. So I need to multiply out by a common. I need integer values. So if I multiply this whole thing by 2, it's going to be 1, 2 hat, 0. All right, let's go to the next one. So let's go to my, oops. So where do we finish here? 1 half, 1 half, 0 minus, where's my start? 1, 1, 1. So again, I'm going to get basically a half. So actually minus 1 half, and then minus 1. And when I multiply that out, it's going to be 1, 1, 2. Right here. What about, what's my final one? I need a red. What about my red? So finish, oops. Finish is at 1, 1, 0, minus the start, which is at 1, 0, 1. And we are left with 0, 1, 1 here. There you go. So that is drawing, or identification from when they're drawn. Let's say that you are asked to draw the following. 1, 2 hat, 1, how about, also do 1 hat, 0, and then finally, let's do like 3, 1, 0. All right, so let's draw my unit cell, and let's just take it one at a time. So if I want to achieve this, let's start with this one here. So I need my finish minus my start, and it needs to equal that. So if I start at 1, 0, right, that's good, finish my start. Actually, but we see this 2. So the 2 already means that I may need to start at a half. Because a half minus 1, because we know that this is going to have to be 0 and 1, because then when I multiply it out, it'll be 2. And then finally, it'll probably be this as well. So I can do a half, actually a half, 0. So that's going to be my finish, my little arrow here. And my start is going to be right here. So I can go just like this. So that would be this value here. What about here? This one's a little bit more straightforward. Finish minus start. So 0, 0, 1, 1. And then this can be 1 and 1. Again, I want to draw these so that they stay within the same unit cell. So I don't want to extend those. So 0, 0, 1. So this is my vector here. And we start at 1, 1, 1. So I can go, zook. There we go. Got it. And then finally, 3, 1, 0. Now that's an interesting one. But again, same procedure here. So finish minus my start. So if I do 1, so I need to multiply out by third. So if I do, for example, if we do 1/3, 0, and then we do 1, 0, 0, 0, actually, let's not do 0, 0. That's boring. Let's do 1. Let's do 1 here. So if so that's my start here, and then my finish is at 1, 1/3, 1, so it'll be like this. There you go. Finish minus start. Those are your crystal directions. Now, in cubic crystals, we have some directions which are what we call crystallographically equivalent. So, which means if we just kind of rotate our crystal, we can't distinguish them. We already encountered it with our 1, 0, 0, right? So we saw I have a 1, 0, 0 here and 1, 0, 0 here. And that's because for cubic symmetry, I can rotate and have all of these be, if I blindfolded you, you couldn't tell the difference. So we'll have this whole group, they are crystallographic equivalent, so we could write these as this. Same thing with, we could have 1, 1, 0. We can have 1, 0, 1. We can have 0, 0, 1, or 0, 1, 1. And then we could have the minus version of those, right? So those would all be crystallographic equivalent 1, 1, 0. And the same thing with 1, 1, 1. and then we could have 1 minus 1, 1, 1. You know, you get the picture. And then that would be crystallographic equivalent of 1, 1, 1 direction here. So those are crystallographic directions. So next time, we are going to get into crystallographic planes, which have a little bit different set of rules. So we'll see you all next time. Thanks. Bye.